Today I wanted to talk about some proofs. And now that I've prepared the lecture, most realistically, we're going to focus on the proofs that just on the, I had two lines in mind, and we'll see how far we get. But there's this time-honored practice of looking at restriction maps to subgroups, cohomology of subgroups. That's a very standard technique, and we actually saw it already when we were talking a little bit about characteristic classes, more as a way to preview exactly this topic. And then the other thing maybe I'll be very brief about is Fox-Neuwirth cell structures, which give rise to really to resolutions in algebra. And these have come up in sort of in the infinity category world now. So all the better to say something about them if we can. So, but let's talk about restriction to subgroups. So if I have a subgroup, then the simplicial model is functorial. So I could use this, but I'm going to model this map from BH to BG as a covering map because I can just use the same EG as I had for G, but now take the quotient by H, and that's another model for BH. And then let's note that in general, if I have a covering map of Y, say, over X, and it's finite sheeted, then there's a couple games I can play. If I trivialize this with respect to some cover U, that's part of the data assumptions of a covering map. In other words, if I have an open set in that cover of X, then its preimage is going to be a disjoint copies of U. Then I can define the transfer map in homology at the chain level. What is this? Pardon me. And what it's going to do is at the level of chains, it's going to take an in chain in X, say subordinate to that U, and then going to give me an in chain in Y, and I just have to think of a single generator, and I'm going to just look at the sum of sigma tilde, so that is the pi of sigma tilde is sigma. So these are just all the lifts. So you're taking you picture a simplex in the bottom, and you look at all the lifts over it. And so this is the transfer. It's often called pi shriek. So that's what pi shriek is doing. Alternately, and we're just mainly going to use this definition, but alternately, I can take in cochains on Y in the manifold setting and map them to in cochains on X, extending the following map. Just take my tome class, that's something represented by a submanifold, and well, it'll still be a submanifold, or well, maybe, yeah, it should still be a well, anyways, in some cases I just look at the image in the cover, and that natural map is a wrong way map in cohomology. So this is often called pi upper star. Pi upper shriek. I should have called this one pi lower shriek. So that's the transfer. And it has the property that, which is obvious from the first definition, that if I apply transfer, wait, I got it exactly wrong. The shriek often goes in the direction you're doing incorrectly, quote unquote. By the way, let me open the chat just so people can keep me honest. So, and so then this one is going the wrong way up from the base to the fiber. So if I apply that and then apply the usual map, this is going to just be multiplication by the number of sheets. So that's a crash course on the transfer. Again, these are, sometimes it's developed fairly mysteriously. Actually, this is duality more generally, but this is a case, well, the first definition is a standard one. You get the following consequence of just the existence of the transfer. Well, so corollary. So let HG be a p-Sylow. And let's talk about all homology and cohomology with mod p coefficients. Then multiplication by the number of sheets in this case is going to be multiplication by something prime to p. And so that's an isomorphism with mod p coefficients. And so what that will mean then is that the homology of BH is going to surject onto the homology of BG. Again, this is mod p coefficients, or the cohomology of BH. We're going to get an injection from the cohomology of BG. So you can consider p-Sylows in general as a good way to get started on the cohomology of a group. Sorry, let me move around a little bit. There we go. There's the corollary. No, tome cochains doesn't require a good cover. That's what we needed for the chain description. That was a question Michael just asked. Sorry about that. You need that for this good cover, but the tome cochains is much more of a differential topology. Of course, it does require having manifold, whereas the definition I gave in homology doesn't require that. Good. Okay. So what's our main example? We're going to hopefully understand really well the homology and cohomology of the fourth symmetric group. Okay, it's a key case. And the 2-Sylow, in this case, maybe is not that familiar to people, but it's called the wreath product of S2 with S2. And the way I like to play with that, is, well, the way you can see that explicitly is if S4 permutes 4 things, call them 1, 2, 3, 4. And what this group does is it's got a subgroup that permutes 1 and 2, a subgroup that permutes 3 and 4, and then what it can do is permute both of those. And so really what you have is a little short exact sequence of groups where the product sits inside the wreath. So on classifying spaces, what I'll say is if you've got a fiber sequence from, well, let's remember that BS2 is RP infinity. So RP infinity cross RP infinity maps to the classifying space for this wreath product, which fibers over RP infinity. So the way I like to think about this geometrically, and we'll use this, is I've got RP infinity, the base. I'm looking at pairs of antipodal points on S infinity. Oops, let's use maybe another color. So these are antipodal. And each one of them is going to be decorated by a point in RP infinity, which I can think of as a line or I could also think of as a pair of points itself. I'll just draw them as lines. So each decoration, this is sort of sitting inside our infinity. So those are, again, it's just 2 points on the antipodal points on the infinite sphere, each of which is labeled by themselves by a point in RP infinity, and as you sort of go around, those get exchanged, so to speak, in the monodromy. So that's this space. And so the other way to think about it is that, right, this is the same as ES2 crossover S2 with BS2 cross BS2. Okay, and in general, ES2 crossover S2 with X cross X acting diagonally is what's called D2X, the second extended power. That's what Steenrod named it. He showed us, and I'll maybe make a comment on that in a bit, he showed us that you can define Steenrod operations using the cohomology of this space. So this is something that you can then very explicitly get cell structures. If you take, say, the equivariant cell structure on S infinity, which start with S0 with 2 points exchanged, and then S1 with then 2 1 cells, which are also exchanged, S2 with 2 2 cells exchanged. That's a standard cell structure. And if X had a cell structure, you get a cell structure on this extended power. And so what we can do is talk about in general, what is the homology and cohomology of the extended power? So this is very much a part of the story of both homology, cohomology of symmetric groups, and then also why they have such importance in topology in general, because again, this is part of the story of Steenrod operations. So what's the general statement? And we're gonna talk about both homology and cohomology of this extended power, and it's going to have. So let's give this a cell structure. Let's assume there's a cell structure here, and or here. So we're going to have cell structure. We're going to take the chains, the equivariant chains, and the same thing on S infinity. That's a standard resolution of the group S2 or Z mod 2, cyclic order 2, cross the tensored with the chains on X, tensored with itself. That's of course the product. And then we're going to quotient by S2. And this is going to help me just sort of name some things. So this is a basic calculation. I won't go through it entirely. It's something that every topologist should do at some point in their life, so to speak. But let me just give the answer. So this has additive basis. In homology, you have things of the form 1 tensor alpha, tensor beta. And you also then have where alpha and beta are cycles in the homology of X. And let's just say spanning set if I don't want to keep too much track of a basis, because in fact, I would have to order these. These both map to, right, so alpha less than beta if I want a basis, because these map to the same, or I can just say this is equivalent to this. And then the more interesting thing is that we can take the I-cell and in mod 2 homology, this ends up being a cycle. And what I'm going to call this, so let's give these names. I'm going to call this alpha star beta, and I'm going to call this phi I of alpha, and it's a formal Dyer-Lashoff operation, if you will. So the idea back from a couple lectures ago is EI means sort of, if I'm thinking about this configurations model, 2 antipodal points on S infinity, EI sort of goes through an RPI, so pairs of antipodal points restricted to the I sphere in all possible ways. And now alpha is your cycle in X. And so you're taking that cycle, you're multiplying it by itself in over all possible ways in I dimensions. So this is a formal Dyer-Lashoff operation. And we'll say, or Kudo-Araki actually. And I'll say why it's formal in a second. Right. Let me just actually let's go right to that. So then, so this is the homology story. I'm going to tell the homology story first. And so then what happens? Again, this is just a calculation that if I knew the homology of X, here's a way to understand the homology of D2X. Notice that you get the homology of RP infinity when X is a point. I'm not sure if I need to be reduced here. I think so. In any case, what we know is then that the homology of the wreath product maps to the homology of the group surjectively. And the claim is that, let's remember that so let Qi be the non-zero class in Hi of RP infinity. Then we have this Qi star Qj is in fact going to go to Qi Qj. But then the more interesting thing is that this formal Dyer-Lashoff operation on Qj is going to go to, well, Qi of Qj, which we were often calling Qi comma j. So this map from the p-Sylow in this case is sort of saying we've got these Kudo-Araki operations, and the homology of the wreath product is sort of the formal object on those. But then, so what that really says is then that from this perspective, I claim that the main work in establishing the homology is establishing Edem relations. And then there's further work that you really need to some bookkeeping, but from this group homology perspective, you need to also somehow prove that there's no further relations. But really, from this group homology perspective, the wreath products generally they give you these formal classes, wreaths of of the homology of RP infinity, which give you longer and longer Dyer-Lashoff operations, because in fact, the p-Sylow of Bs to the n is an iterated wreath product. So, but these Edem relations, they're tricky, and to be honest, if you have a great way of establishing them here from a much more, from a elementary or even just generally clear viewpoint, and I don't mean sort of right formalism, there's great, a wonderful survey by Joël and Bisson, and I've seen some expository work of Lurie, et cetera, that sort of packages the Edem relations really well. But, you know, so, but I invite sort of something which would be more direct. So what is the first Edem relation? It's that Q2 on Q0 equals Q0 on Q1. So in this wreath product, we have antipodal points with RP infinity labeled by, as I said, either lines, or we could think of those lines as two antipodal points on some other S infinity. We can actually then map that in a natural way to get a configuration of 4 points. So what does this one look like under that map? So is this my RP2? And then if you, and then we would have, well, Q0 is sort of a constant. So I just have pairs of antipodal collections of 2 points. I imagine this sort of even happening, say, normally in S3 or something like that. And so this is a cycle. This is an RP2's worth of points in configurations of 4 points in R infinity, or lower, if you will. And then what we're saying is that I can also take an RP1 cross RP1, and that produces 4 points in a different way. And these end up being homologous. So here's 2 explicit submanifolds of the configurations of 4 points in R infinity, or sufficiently high RD. And I'm, of course, using the unordered model because this is happening in the homology of the fourth symmetric group. And yeah, I still don't have a good explanation for that. I'm starting, by the way, and we'll see what I get to, or people can always talk to me another time. I've got a couple different other ways to start establishing Edem relations. It's kind of something that's question that's interested in me for a while. Can we understand these very basic relations in topology in a more elementary way? And so far, directly thinking about this picture, no. But if anybody else has a good cobordism between that RP2 and the torus, I'd be very interested, or even other proofs. What I'm going to do instead is let's move back up now. I'm going to switch now to cohomology. Additively, the story is similar, but let's establish some notation. So I think that from the ground proofs are actually easier in cohomology. And that's because there's some other kinds of calculations one can make, very classical calculations. And what I want to do is take this wreath product, and I claim that there's a couple interesting subgroups in here. The first one is, well, it's the the first group in that little fiber sequence that we said, the S2 cross S2 includes in the wreath product, and the quotient is S2. And this one I'll say is 1 cross delta. It's across the diagonal. Let me be very explicit. This first one is generated by just 1, 2, or 3, 4, or 1, 2, 3, 4. Those are the 3 non-zero elements. Here, the 3 non-zero elements are 1, 2, 3, 4, or 1, 3, 2, 4, or 1, 4, 2, 3. So that's sort of very explicitly what those two subgroups are. And I claim that this is injective on cohomology. So the S4 maps injectively to the direct sum of these. Well, since they're isomorphic, let me give you other names for them. This first one I'm going to call V1 cross V1. And the second one I'm going to call V2. And they fit in a general discussion of these are the elementary abelian 2 subgroups. So this maps injectively to the direct sum of the cohomology of V1 cross V1 and the cohomology of V2. What good is that for? And so why? So after the claim, after proving the claim, how are we going to use it? Well, let's remember that we showed that the cohomology of G maps not just to the cohomology of any subgroup, but it happens to map to the what's called the Weyl invariance, and that's just the normalizer. So here WH is the normalizer of H mod H. I proved this using the quote-unquote particle model for BG a few lectures ago. And again, that was first seen in the cohomology of ON, which are Friend's characteristic classes, but this is true much more generally. Now, the cohomology of both of these groups is just a polynomial algebra on 2 letters. But the first Weyl group is just going to be S2 cross, just going to be S2. You're looking for the sort of external automorphisms, and those 2 factors of V1, I can interchange them. And so, so if I'm looking at the Weyl invariance, these are classical symmetric polynomials. While, so for V2, of course, I'm also going to get polynomials in 2 variables because it's RP infinity cross RP infinity again. But in that case, well, so what is V2? The inclusion of V2 in S4 is the inclusion you get by having F2 squared, in other words, that little 2-dimensional vector space over F2, act on itself by addition, action on the left. And well, it's acting on 4 things, so then we've got some embedding. And again, here's where you can look, if I think of those 4 things as 0, 0, 0, 1, 1, 0, and 1, 1. Then acting by 0, 1 will exchange these two, those sets of 2 points. And acting by 1, 0 performs the exchange of these two. And I gave you what V2 was as a subgroup in terms of simultaneously permuting 1 and 2 and 3 and 4. So I could let, for example, this be 1, this be 2, this be 3, and this be 4. And now we see that 0, 1 acts by permuting 1 and 2, simultaneously permuting 3 and 4. So if you see this linear model for that subgroup, then which is really wonderful, and I think not nearly appreciated enough that you've got these beautiful elementary abelians there. Then the claim is that the Weil group, well, what's a way you can permute things compatibly with a linear model? That ends up being the second affine group on F2. Or sorry, that's the normalizer. And then the Weil group is GL2 F2. And then you are led to calculate. So the cohomology of BS4, when it restricts to the cohomology of V2, which is this ring, but I'm going to take the GL2 F2 invariants. And so you can ask that question: what are polynomials that are invariant under GL2 F2? And this is a lovely classical question. It was answered over 100 years ago by Dixon, the same Dixon for whom postdocs at University of Chicago are still named. And one thing to note is that inside GL2 F2 you have permutation matrices. So these are at least invariant with respect to exchanging x1 and x2. So these would be the off diagonal 0, 1, 1, 0 matrix is going to exchange x1, x2. But there's more. You can have, for example, the matrix 1, 1, 0, 1 or something like that. And you see that there's fewer invariants. Than for symmetric polynomials. So in particular, look, you can take x1 to x1 plus x2, and then x2, say, goes to itself. X2 goes to itself. And then x1 plus x2 is no longer invariant. It's a symmetric polynomial, but that's going to go to x1. There's a little 3 cycle there, right? And so so you start from scratch. Well, you know things have to be symmetric, but here's actually the most basic one. Again, we're going to look at that first, the generating set and the vector space they span. So that's x1, x2, and x1 plus x2. And if you just take the product, then GL2 F2 permutes those three basis elements, and so that's in degree 3. That happens in general. If I look at GL3 F2, there's a degree 7 invariant by taking everything that's non-zero. There's ones that you can derive from there. They're actually in lower degree. So the other one also have x1 squared plus x1 x2 plus x2 squared in degree 2. And Dixon shows that, for example, the invariance here are isomorphic to, let's call these, they have lots of names in the literature, so I'll just call this D2 and this D3. The other way around, this is D3 and this is D2. And Dixon shows that this is actually polynomial, which is surprising once you get to this further into invariant theory. It's polynomial and generated by these invariants. And so the idea will be that, in fact, let me finish off the idea and then we'll go to proving the claim. So moreover, if I take V1 cross V1 and V2 inside of the fourth symmetric group, there is a subgroup there. So you're not exactly mapping to the direct sum, you're mapping to some, in that side you'll have there'll be a limit or a co-limit. In cohomology, we're mapping that way. Yeah, so you'll map to the limit. So, so the cohomology of BS4 maps to the limit of the cohomology of these V1 cross V1, BV2, and this, let's call it S unimaginatively. There's a diagram, let me just draw it out. And the claim is that this is actually an isomorphism. So we know it's injective by, well, the claim is that it's an injective, but it's actually an isomorphism, and I'll prove that for you by producing enough cohomology. So, so the promised proof. So we'll first show it is injective by claim, or that is the claim, and then we'll produce the cohomology to show isomorphism. And believe it or not, and then I should say something about this, in general, the Humph ring presentation, plus the arguments that we'll give for these parts, allow for the generalization of this. I should say, before I forget, well, we're going to prove the claim. It's due to Madsen and Milgram. Well, let me go over to the other board and then make that note. So, so again, the claim is that if I'm looking at, I'll draw it the other way. So I've got S4, and then I've got V2, or actually I was listing first V1 cross V1 and V2, that the cohomology of BS4 restricting to the direct sum, cohomology of BV1 cross V1 plus the cohomology of BV2 is injective. And let me just say that this is true in general, that the cohomology of BSN injects into the direct sum of the cohomology of the elementary abelian subgroups. And that's a result sorry, let me decrease this in size a little bit. That was originally proven by Madsen-Milgram. And then it also begs saying that in much more generality, BG for G finite into the cohomology over A elementary abelian of BA. Well, BA is elementary abelian just means, say, Z2 cross Z2, etc. If we're working at the prime 2, Z mod P cross Z mod P, those cohomologies are either at the prime 2, it's polynomial. At the prime P, it's polynomial tensor exterior. Let's just talk about the prime 2. So polynomial. Well, one thing is the cohomology of BG forms a ring, and if I map to a polynomial ring, then anything that is nilpotent has to map to 0. And Quillen showed this is injective modulo nilpotents. Of course, the algebraic geometers would, and commutative algebraists would say, oh, okay, the spectrum is isomorphic in a sense. So yeah, so this technique that I'm saying is the best way to go for, and I'm just going to show you for BS4, is part of the standard way that a lot of group cohomology has been done over the years. But let's get back to this claim in the BS4 case. So let's again, sorry, let me copy once more. So I've got the cohomology of BS4. And really what I wanted was, well, because it's the p-Sylow, it suffices, of course, to consider BS2 wreath S2. Let's first think about BV1, V1. So now we talked about the homology of the wreath product. Now let's talk about the cohomology of the wreath product. Additively, it's going to be the same story. But now we're going to look more at multiplicative structure. So what is this? What is the basis here? I'm going to say there's two kinds of classes. One which I'll call xi transfer xj. So in this model of RP infinity, so this is going to be the tome class of, I have a point on RP infinity, which are two antipodal points on S infinity, each decorated by a line, or say themselves 2 points. And now I can ask, is that line sitting inside some codimension I or J set? Okay, so this is a tome class where one line is inside R capital N minus I, where another is inside R N minus J. And notice that that is symmetric, and I'm using it with the same name as a transfer product because, in fact, that's sort of compatible in this picture. So there were two basis elements in homology. This would be sort of dual to the Qi star Qj. Let me next, we have something that I'm going to say is of the form y to the I times x to the j divided power 2. And it's again notation that I'm using to be suitable for generalization. And what this is the tone class of you have the red points are now sitting inside RP n minus I, whereas each of the blue lines are inside RP n minus J. So there's an explicit cell structure that you can use to talk about these calculations. I'm going to talk about tone classes because I'm going to use those. And then the claim is that we also have cut products now. So x to the I, x to the j, cup, x to the k, x to the l is, again, you can work this out geometrically, x to the I plus k, x to the j plus l, plus you add them the other way around. We don't know which, we've got a symmetry between the lines. We don't know sort of which red point we're on in this condition, and so it can also be x to the I plus l, x to the j plus k. If you're paying close attention in the cohomology of symmetric groups, you would also expect some of these to be 0, but in fact, just like our the Edem relations in homology, there's some formalness about this this O dot product, which makes it differ from the actual O dot product. And then we have, well, for the other kinds of class, we've got our generators. For the yi, we've got y1 transfer, or sorry, times x0 to, and we also have y to 0 times x1 2. And then the reason they're generators is yi transfer xj 2 times y, say k transfer xl 2 is what you would expect. Y plus k transfer x j plus l divided power 2. So, but the key thing is that we're going to think about these generators. Great. And so now we can work away at our calculation. And there's a couple ways you can do this. You can try to pull back some of these maps. Again, it's RP infinity cross RP infinity is included in this, is a fiber of this fiber bundle. And so, so it's actually pretty immediate, or you could evaluate on homology. But either way, we have that. So let's let, in the cohomology of BV1 cross V1, let's say that that's generated by, say, a Z and a W. This is just RP infinity cross RP infinity, our good friend. And I claim that xi, xj is going to go to Z to the I, W to the J, plus Z to the J, W to the I. So that's, again, you can read that off of the conditions that are defining these submanifolds. You can read it off of cell structure. That inclusion is cellular. Again, I prefer the geometry. This x to the I transfer x to the j says that one line is in a codimension I linear subspace. Another line is codimension J, whereas the inclusion is breaking that symmetry. It's a, so yeah, let me just say, what is this map? So this is in here. The map from V1 cross V1 to S2 wreath S2. In this geometric model, I can fix my red points once and for all here, and then I just have a pair of lines or a pair of points there, and so this one, once I fix those two, this one is determining the line on the left, whereas this one determines the line on the right. But if my condition in the wreath product, because those can move around, my condition has to be symmetric, then the this commutative product xi transfer xj, so to speak, has to go to this symmetric polynomial. Okay, so, and that's injective on that piece. So we see that this restriction is thus injective. This one restriction is injective on these subbasis. And so we focus now, and here's the key calculation. And there's a lot that you can deduce from this one little calculation. You can get some of Steenrod's results relating these to Steenrod operations. You can deduce the Edem relations and things like that. But we're going to be, again, I think we're going to be limited for time. And so what is the key calculation? Now I've got S2 cross S2, which is my V2, included in S2 wreath S2 as 1 cross the diagonal. And what I have to do is I want X2 in H upper 2 of the wreath product. And I want to know what it goes to in cohomology here. And X upper 2 says that both lines, again in this geometric model, both lines are, now the red points can be anywhere, but their blue lines are both in a codimension 1 subspace. So they're in some Rn minus 1, so to speak. And what we can do is take the homology of S2 cross S2, or Rp infinity cross Rp infinity. I'm going to just use kind of silly notation. This is, if I care about H2, I'm going to understand how this pulls back by evaluating it on everything in H lower 2. So this is the span of a Z on the first Rp infinity, that's just an Rp2 included there, or a Z1 cross W1, or a W2. So these are just Rp2 or Rp1 cross Rp1, or another Rp2. And I'm not gonna, I'm gonna omit the inclusion map as we discuss this. So the question is, what is the value of X2 on, say, Z2? And that means that, so Z2 is allowing the pair of antipodal points to go anywhere. It's fixing, it's constant on the lines. So remember that these lines aren't happening in the same space, quote unquote, as the S2. There's sort of a vector space attached and the line is there. But in any case, if the line is constant, then we're going to choose it to not be in that codimension 1 space. And so we get that this equals 0. Whereas this x2, if I evaluate it on the class z1 cross w1, that means now I'm allowing my antipodal points to, so here they varied over all, so vary over S2. Now these are just going to vary over S1. And a key thing is that you have to, the map is supposed to be the diagonal map. So in other words, the W1 is going to allow the line to go over some other S1. And we're supposed to map diagonally. That's not going to be good for transversality. So we're going to map this in by diagonal. But not transverse. So we must deform the diagonal. And how are we going to do that? In this deformed version, we're going to start, well, however I do it, let's say here, let's actually make these blue lines sets of points. So wherever I start here, suppose I naturally wanted to be up and down, I'm going to choose, so these were supposed to be, instead of diagonal, so instead of diagonal, we offset them. And I could only do one. I could have the top one just lean to the right, so to speak. The bottom one could be up and down. Let's even do that, because that's, again, I don't have to, do it equivariantly, even though the original diagonal was equivariant. The deformation is definitely not going to be. So if they naturally, my first inclusion had the top point straight up and down, I'm going to offset the diagonal. Let me indicate that in green. This is the offset. But the point is that as this top red point comes to the bottom and this other red point would go to the top, at some point this is going to be straight up and down. So even though this is set off at this point, eventually it's going to be to the left. That's another reason maybe to draw this bottom one to the left, if you will. And so at some point in between, as the top has its offset decrease and the bottom one has its offset increase, their offsets will match somewhere in the middle. And that happens exactly once, and then they will be as well in a codimension 1 space. And so what we get is that this equals 1. And finally, this is a really fun one because now we just have 2 copies of RP2. So in other words, the red points, let me draw it consistently, the red points are fixed. The blue lines are just elements of RP2. Again, this must be deformed. Well, if you think about it, so for every, this is a diagonal copy of RP2. So RP2 is mapping into a product of RP2 with itself diagonally, or RP infinity cross itself diagonally. If I'm going to deform it, then really it's equivalent to giving a section of the tangent bundle. That's because, again, I'm for every point in RP2, like say, if that point is x, I've got x, and then this is a deformed x. If it's close by x, then I could think of that as the exponential map applied to some tangent vector to x. Well, then you get the classical theorem that that such vanishes exactly once. And then when it does vanish, I will be in that diagonal subspace, and I'm going to get 1. So this ends up being a bit of a calculation, but once you've got everybody in front of you, then you see that x2 to the I maps injectively into the cohomology of this BV2. And let's remember that, I think I didn't even say it, but then the y to the I also maps injectively, and you just calculate where everybody goes in this ring homomorphism, which I've run out of time, but I'll state that. And that's the kind of technology that underlies then these calculations. Ultimately, let me then summarize. So all together, let's do it this way. The cohomology of BS4 restricts to both the cohomology of BV2 and the cohomology of BV1 cross V1. And we had different additive bases here. So this kind of additive basis, it's going to go to 0 here, and it goes to things like x to the I, y to the j, plus x to the j, y to the I here. Whereas we had 2 special classes here, and this is going to go to the second Dixon class. This is going to go to the third. Remember, that's, for example, maybe I should use x1, x2. Sorry, let's, or maybe y1, y2. And this, it goes to, for example, if we use x's here, x1 times x2 times x1 plus x2. I haven't justified that calculation for you, but it's very close. This has to be injective. This, let's recall that this is represented by 4 points in our configuration, which sit inside Rn-1. So the little calculation you must make, and I've made this once already, is that this evaluates to Q11 non-zero, because Q11 is this kind of picture, similar to what we were just drawing for the wreath products. And so exactly once in such a picture, do we have the 4 points lining up? So that implies that, and this on, say, Q1 star Q2 is 0, because Q1 star Q2 would look like that, and at no point can 4 points come together. And so what this ultimately implies is that this must map to D3 because it's non-zero, the map's injective, it has no place that it can go. And yeah, and so ultimately you can take the Madsen-Milgram detection theorem, take some of our explicit homology and cohomology generators, and then call it and then collect everything and see that. So that's right, because nowhere else to go. And you can prove that our Hopf-Ring presentation is a valid presentation ultimately through that injectivity to elementary abelian subgroups, and then some key calculations. And that injectivity can be proven different ways. Again, you can appeal to Steenrod's original work and look at the, it comes down to some facts about Steenrod operations and RP infinity itself. I gave you a much more elementary argument just now, but either way, you get that injectivity, and then you show that that you must map to certain Dixon invariants or other places, and ultimately show that you hit everything that you can. So that's it's not entirely easy, but it is fairly elementary. I wanted to, and I still will, I'm going to go over, I understand, let's make sure anybody who has questions about this can ask questions, and I'm going to go to, pretty sure I had, there we go. So I'm going to go to where I had some questions, because we'll wrap up symmetric groups. I could talk about them in another 10 lectures, really, in case you didn't figure that out already. Great. So I wanted to leave everybody with this topic. There's a lot more that can be done. So the QIs and these gamma Is, the QIs span homology and their products. The gamma Is span cohomology with the two products. I don't know how they pair, and I think that would be extremely interesting. I conjecture it's related to the pairing of the Milnor basis for the dual of the Steenrod algebra and the Serre-Compton basis for the cohomology, the Steenrod algebra itself. The other thing that's coming up, Lorenzo Guerra, Paolo Salvatore, and I are calculating the cohomology of these extended powers more generally, with the cohomology of symmetric groups being what you get when X is a point, or depending on how if you smash versus product when X is S0. And it looks like we're developing divided powers operations, but it looks like there's derived versions of those. And I think those are going to be key to understanding the generalized cohomologies of these things, which is very much an open question. What is the Morava K-theory or E-theory? Or K-theory is known by T.S. Siegel, but pretty much any other cohomology theory is not known. I mean, let me go back. Understanding homology and cohomology together, we saw that the wreath products were key to understanding homology. By this detection subgroup result, I'm actually finessing the question of wreath products and cohomology. We're using these VIs and products of VIs. And in some sense, that's that seems kind of, it's like wreath products are quote unquote native to homology, whereas elementary abelians are quote unquote native to cohomology. But it would be good to calculate all of these structures in both homology and cohomology. And I think that could be useful in collecting what one needs to start to understand generalized cohomology of symmetric groups, and then of iterated loop spaces, because I think, as I've mentioned, when you let the n go to infinity, if you're looking at BS infinity, that homology and cohomology is the same as that of loops infinity, S infinity. Here's a very concrete question. Group cohomology is X'd over the group ring of the field with itself. Can we understand these classes? So this would have been more appropriate, say, last lecture, where I gave this basis, but really just understand even the gamma i's. There's some sequence of 2 to the I modules that is over the group ring of the symmetric group, and it would be interesting to understand a good choice of those. That's the extended sequence of 2 to the I modules in the Yoneda model for X. A number of folks, people like Benson, Friedlander, Pefstova, have made the following observation, that group cohomology, X over BG of K and itself, it maps to endomorphisms of any representation of the group ring in the field, the ground field in question, over the ground field in question. And they define support varieties as the kernel of that map. And they've used this to study representations of symmetric groups a bit, but I think there's a lot more room now for explicit calculations in that theory. And then finally, backing up, this transfer product, which was so key in understanding the cohomology of symmetric groups, it's really an induction product. It's the cousin of, and agrees, it's defined by the same stable map as take 2 representations, take their exterior tensor product, and then induce from Sn cross Sn to Sn plus m. And there's similar structures for alternating groups and general linear groups over finite fields, other linear groups over finite fields. So I think there's just room to play with these structures a bit more. GLNFP, though, I tried a little bit and I couldn't. We still know too little about its cohomology, and I think more basically, I for one love to think about the configurations model for BSN, and it would be great to have a similar model for BGLNFP. And I don't know of one yet, so maybe something motivic, or maybe in the right setting there might be something geometric, but there's not a good geometric BG, something like Grassmannian or a configuration space for GLNFP, and I think that makes it hard to get off the ground. Okay, I apologize for going over and for not getting to Fox-Neuwirth, but I'll pause for questions, and then we'll also then stop the YouTube live and pause again. Okay, I will